Electronic Control and Digital Electronics Level 3. Module 2. Session 2.1. Session 2.1 will cover the following content: Important components new to Level 3, Introduction to the Oscilloscope. We will now go through the various electronic components that the students will come across during their study of ECDE Level 3. You can refer to your workbook for more information on these. The components that your students should already be familiar with from their Level 2 studies have also been summarized in your workbook. You should also consult your textbook for a more in-depth understanding. The first new component that students will learn about in Level 3 is the junction field effect transistor, or JFET. A JFET is a three-terminal unipolar semiconductor device. It is available in N-channel and P-channel configurations. You will remember that in a bipolar junction transistor, the output collector current of the transistor is proportional to input current flowing into the base terminal of the device. This makes the bipolar transistor a current-operated device, as a smaller current can be used to switch a larger load current. The field effect transistor, or simply FET, however, uses the voltage that is applied to their input terminal, called the gate, to control the current flowing through them. This results in the output current being proportional to the input voltage. As their operation relies on an electric field generated by the input gate voltage, this then makes the field effect transistor a voltage-operated device. Field effect transistors can be made much smaller than an equivalent BJT transistor, and along with their low power and current consumption and power dissipation, makes them ideal for use in integrated circuits such as the CMOS range of digital logic chips. There is another type of field effect transistor available, where the gate input is electrically insulated from the main current carrying channel. These transistors are known as insulated gate field effect transistors. The most common type of insulated gate FET, which is used in many different types of electronic circuits, is called the metal oxide semiconductor field effect transistor, or MOSFET for short. MOSFETs operate in the same manner as JFETs, but have a gate terminal that is electrically isolated from the conductive channel. A MOSFET differs from a JFET in that it has a metal oxide gate electrode, which is electrically insulated from the main semiconductor channel, or by a very thin layer of insulating material, usually glass. The MOSFET is widely used for switching and amplifying electronic signals in electronic devices. Typical examples include high-powered audio amplifiers, such as those used for vehicle music sound. Its advantage is that it uses very little current as opposed to other similar devices, and is very efficient. Let's now discuss operational amplifiers, or op-amps as they are more commonly called. These components are one of the basic building blocks of analog electronic circuits. We will be discussing these in more detail in a later session. Op-amps are voltage amplifying devices designed to be used with external feedback components, such as resistors and capacitors, between their output and input terminals. These feedback components determine the resulting function of the amplifier, and by virtue of the different feedback configurations, whether resistive, capacitive, or both, the amplifier can perform a variety of different operations, giving rise to its name of operational amplifier. These amplifiers are three-terminal devices which consist of two high-impedance inputs. One of the inputs is called the inverting input, marked with a negative or minus sign. The other input is called the non-inverting input, marked with a positive or plus sign. Op-amps are linear devices that have all the properties required for nearly ideal DC amplification and are therefore used extensively in signal conditioning, filtering, or to perform mathematical operations such as add, subtract, integration, and differentiation. We will discuss op-amps in more detail in the next module. Linear voltage IC regulators are often at the basis of power supply designs, as they are very good at supplying a continuous fixed voltage output. Linear voltage regulators are generally much more efficient and easier to use than equivalent voltage regulator circuits made from discrete components such as a Zener diode and a resistor, or transistors and even op-amps. The most popular linear and fixed output voltage regulator types are by far the 78 positive output voltage series and the 79 negative output voltage series. These two types of complementary voltage regulators produce a precise and stable voltage output ranging from about 5 volts up to about 24 volts for use in many electronic circuits. Voltage regulators are mainly used to regulate the supply voltage to a circuit and to ensure stability. They prevent fluctuations in the changing or intermittent supply from the AC mains and keep the output to the circuit steady at whatever voltage it is designed for. An oscilloscope is a vital piece of equipment in any electronics workshop. It is very important for you and your students to have a good understanding of this machine. Let's watch a video now demonstrating how it works.
We are now going to look at a very important test equipment called the oscilloscope. The oscilloscope is regarded as a technician's third eye and should find a place in any laboratory, workshop, or any environment where a technician or design engineer is working with electronics. I want to show you some of the things that comprise this oscilloscope. Firstly, this is called the oscilloscope probe, a very important piece of the oscilloscope. You get various types of probes. If you use the incorrect probe on a special machine, maybe on a machine that's not designed for this particular probe, you're going to get incorrect results. This is where you will connect your earth point. Another important part is the switch. All the probes have this switch. It's called a ×1 and a ×10. The reason why we have ×10 is some displays are so small that you have to multiply the display by 10 in order to see it. I like to use the ×10 because the display is of a reasonable size and calculations become very, very easy. So when you are about to start using the machine, always make sure that you know where this switch is. Some of the controls that we are going to be seeing, this is the trace. This is the actual trace that's going to give us our measurement. This is called the graticule. They are 1 centimeter divisions. You'll see how this comes into action in a moment. This is the intensity or brightness, if you like. You can see when I turn it, you can actually take it completely off, or you can increase the intensity. Please do not leave it on bright and walk away, because after a while, after a few weeks, you'll find this trace will burn a mark in here. Behind this, there's a screen, and on the front of the screen, there's something called phosphor, and the phosphor will burn through and the line will remain there. So it's always advisable to leave it at a reasonable intensity. Next to that, you have focus. You can see that the focus gives you a nice sharp trace like so. This is a dual trace oscilloscope, which means you can see 2 traces at the same time. You have channel 1, which gives you 1 trace, and you have channel 2, which gives you another trace. I'll just show it to you now. This channel 1, it's on at the moment. This is the lead that's going to channel 1. I go to channel 2. Here's channel 2. But if I want to watch both at the same time, I could do that. I could use this to do some tests on a piece of equipment. I can plug in a similar cable on this side, and I can do tests on a similar type of equipment that's working, and I can compare the waveforms. But for this exercise, we are only going to use channel 1. You can also have a situation where you can chop, where it shows you one and then it shows you the other at alternate times. You have position buttons which can move the trace, in this case up and down, which is vertical. You also have position button here which can move the trace. As you can see, it's disappeared. your horizontal on this side or that side. That's just to give you a centralized position where it makes life easier to make measurements. This is an important knob or control, if I may add. It gives you the times per division, and by using this information you can work out frequency. In this particular oscilloscope, we are very fortunate we have a display that gives us the frequency, but I will show you in a moment how to calculate frequency, and we'll compare the value that we get with the value that is shown on the oscilloscope. Other important controls are trigger. You have internal trigger and you have external trigger. We won't be using that for our exercise. We have something called slope, where you can change the slope. That's normally used for equipment like, or entertainment pieces of equipment like televisions, etc. We won't be using that here as well. Okay, so we have channel 1, channel 2, line, etc. We're not going to be using that here as well. Now, the most important thing that we're worried about at the moment is volts per division. Please do not compare or confuse the small lines in between as a division. A division is 1 centimeter. So from the middle, it's exactly like graph paper. So from there to there is 1 centimeter, which is 1 division. From there to there is another division. From there to there is another division, and so forth. And on the horizontal axis, we also have that as a division. From there to there is another division, and from there to there is another division. Now, it's important to always calibrate your oscilloscope. We use this small gray button here. Listen for a click. That is in most cases calibrated. Channel 2 also has one. If you get it into that position, chances are that it's calibrated 100%. You might have to make slight adjustments by bringing it back and forth, but for our exercise, that's not going to be necessary. Now, if you look around here, you will see lots of numbers. At the moment, there's a marker on each control knob here. Here you might not see it clearly, it's white in color. Try and bring this one up here. You can see there's a white line there. This one is set on 1. If you look carefully, it's got 1. You can go to the next level, that will be 0.5. If you go to the next one, it gives you a different number, and so forth and so on. I want to set it on 1. What does that mean? It means that if I get a reading, I must look at this number and see where it is set. This tells us it's 1 volts per division. It is 1 volt per division. So if this trace goes up, when I'm doing my measurement, if it goes up there, it means that it's 1 volt, not forgetting that you have to multiply it by 10, like we explained. So it becomes 10 volts. It's a very critical thing to remember. We tend to forget that this multiplied by 10 is a very critical factor. So I'm going to leave it on 1 for the sake of ease of understanding, rather than going to various others like 0.5, 0.2, which makes our life a little bit more difficult. So I'm going to centralize my trace. This is my position. You can see the arrows here telling you it's vertical. I like to bring my trace to the middle. I could actually make measurements with a trace there or there or there, but the point is, if I have quite a large voltage to measure, then the trace will disappear from the screen, and that's going to make it difficult for us to see anything. So we're just going to get this there like so. We are only going to be focusing on channel 1 at this stage, and we are going to use this machine to give a reading on DC, how we're going to measure DC volts, and how we're going to measure AC volts, and how we are going to calculate frequency and RMS value by using this oscilloscope. It's a very useful piece of equipment, and knowledge of how to use it makes life a lot easier, especially in the repair or design environment.
End of the video. We'll be right back.